All right, DE Calculus class. I am ready to show you guys lesson 4.3, which is area and definite integrals. And we're going to find the area under a curve on a closed interval. So we did this yesterday, approximating with Riemann sums using some rectangles. To find this area from here to here, we made us some rectangles and we took those, we found the area of those, and that was an approximation. Well, today we're going to use what's called the fundamental theorem of calculus to find the exact area from A to B on a given interval on this area under the curve exactly. So let's get rolling. I'm going to try to go through this quick. You may have to pause in order to keep up and fill in some of your notes as you're going, and then we'll have a few practice problems for you guys to work on today. So first off, whenever you're finding the antiderivative of f of x, they're going to call the original function f of x. All right, and then we're going to evaluate that using a and b by plugging it in. So we're going to have notation that's going to look something like this. From a to b, the derivative of f of x is going to be plug in, find the antiderivative, and then plug b in first, and then subtract what you get when you plug in a. And that will be the area under the graph, under this interval. Boom. So here's a little demonstration. That this area under this curve is A, B. So find the antiderivative of the function, of this function. Plug in the ending, the rightmost interval. Subtract the leftmost interval, plug those in. Okay, so definition of a definite integral. Definite meaning it has these bounds, A and B. Next chapter, we'll look at some that go to infinity, and those are indefinite. Or if you're just wanting to find a derivative, actually, like we did in the last section, if you just want to find the antiderivative of that, that's an indefinite integral. So definite integrals have these bounds from A to B that we're finding, and find the antiderivative, plug in B minus plug in A. So if we want to find the area under the curve of x squared plus 1, let's just see, that looks something, let's see, x squared is a parabola, we're going up 1, so it looks something roughly like that. Looks like we're going up here on the negative side, so if we want to go from negative 1 to 2, we're trying to find this area right there. So you can find the antiderivative, plug in 2, plug in negative 1, subtract, boom. So we've already found the antiderivative here. It was x cubed over 3 plus x. So then plug in 2, plug in negative 1 into this big f of x, capital letter f of x, to get the area under the curve. Which is demonstrated here, 6. Again, moving fast. Pause it if you need to. Alright, so I'm not going to do the quick check. I don't think you have them on your notes anyways, but if you needed to calculate the interval from 0 to 5, you would do the same thing that we just did, but you would put in f of 5 minus f of 0, boom, which is shown right there. If you wanted to go from negative 2 to 2, you'd put in 2, put in negative 2, subtract, Boom. Shortcut, well, this is a symmetrical graph. So from -2 to 2, it's symmetrical. So actually you could just find one of these and multiply it by 2. From 0 to 2 and multiply. That could be a shortcut. Okay, so now evaluating from a to b of x squared dx using the antiderivative. So we're just plugging in letters here. All right, so real quickly, let's knock some of these out. What's the antiderivative of this one? Would be x cubed over 3 minus x squared over 2. And we're going to go from 4 to -1. So that means plug in 4, plug in -1, because we've already found the antiderivative. That's what that notation means. F of 4 is f of -1. Let's see if we have this one worked out all the way over here. Yeah. So that notation means plugging in 4 for x, subtract, so this is like f of 4, big F, because we found that antiderivative. -1, subtract, result, 14 and a sixth. All right. Next up, we have e to the x, which antiderivative of e to the x is e to the x. And we're going to go from 0 to 3. So that's going to be e to the 3 minus e to the 0, which is e to the 3 minus anything to the 0 power is 1. That's as far as we need to go, because if you put that in the calculator, you're going to get a decimal. So you can stop right there. And then I'm just going to keep going to the last one worked out here. So antiderivative would be of 1 is x plus 2x squared divided by 2. So that ends up being x squared minus a natural log of x. All of that from 1 to e. So you're going to plug in e into all these, just that part. You're going to plug in 1 to all these, subtract. Doesn't clean up beautifully. You end up with something like this. And you can stop right there. So you don't have to get a calculator and type in e. Okay, so these quick checks, I am not going to work those out for time's sake. But if you want a little extra practice and want to know the answers, there's number 1, 2, and 3. Feel free to pause as needed. All right, now the fundamental theorem of integral calculus. Well, it just says that if you did what we did yesterday with the Riemann sums, and you found these rectangles of different sizes under the curve, and then you made this distance, or you made the number of rectangles get smaller as n approaches infinity. So yesterday we did 6 rectangles, 12 rectangles. You just kept going, and you made more and more and more and more rectangles until as n goes to infinity. So it ends up being all the rectangles under here that you're in fact just finding the integral from a to b which is the area under the curve from A to B. So the integral from A to B, definite integral of f of x dx equals big F of B, which is antiderivative, minus big F of A. The second B is the second interval in our range, and A is the first. Plug those in, boom, just like we've been doing. So that essentially is the fundamental theorem of calculus. Just tells us that on any interval from A to B, you can find the area under the curve by finding the integral or the antiderivative of f of x from A to B, and that's it. So we can practice that, and this is a little application problem, but we have the function 1 over x, and it has to do with profit. So if you wanted to find this area under here, which would be the profit if you drove, this is in 1,000 miles, from 1,000 miles to 4,000 miles. So that's going to be an integral from 1 to 4 of the original function is going to give us this area under here, which would be the profit from 1,000 to 4,000 miles. And let's see what we got worked out under here. Oh, so that antiderivative of 1 over x is ln of x. And then we plug in 4, plug in 1, boom, boom, boom. And this is in profit per mile traveled, and x is the number of miles traveled. So total profit ends up being $1,386.30 when you go from 1,000 to 4,000 miles traveled. All right, now we're almost done with this stuff for today, and then I think this is the last example for today. So predict the sign of the integral by examining the graph, then evaluate the integral. Well, this area, if we wanted total area is always positive, so technically we'd have to make these positive and add them up. But for a function, this area, this value ends up being negative down here, and this value ends up being negative below the graph, and this value ends up being positive. So just from guessing, there's much more area down below, so we would guess that this integral from -2 to 2 is going to have a negative. So predict the sign, we would predict that this is going to be negative, is our prediction, because there's more area below the x-axis than above. And we could evaluate that to actually find that. It just helps you know if your answer's kind of on the right track. So if you want to find, well, we need to find the antiderivative of this. So add 1 would be 4, divide by 4, the new power. Add 1 would be 2, divide, it's 3/2 x squared. Add an x, or add, well, that's x to the 0, so add 1 would be x to the first, divide by 1x. Then plug in from negative, the integral is from -1 to 2, so plug in 2. This is big f of 2. Plug in -1. Subtract those. This is f of -1, and you get a negative value. All right. Well, I want you to do your best. I know I'm out. I know you will do your best on these, and we will resume tomorrow.